The first question about a plane accelerating uniformly is what we've been calling a SUVAT question. So with all SUVAT questions, the best way to start is to write down SUVAT. And we go around and find the values. So what does it tell us? It tells us what the velocity was at the beginning of the question. So the value is there. So I'm just going to put a tick. When you're doing it, you actually write in the value. It also tells you what the velocity increases up to. So again, you can write in the value, but I'm just going to tick it to show that we know its value. It tells us how long this thing takes. You write in the time, I'm just going to tick it so that we know that the time is known. And then what remains? Well, we're asked to find the acceleration. We don't know the value, we need to find it. The other thing that we don't know, that we aren't asked to find, we don't know the distance travelled. That isn't part of this question. So we then, of course, need to have a look at the equations. We know u and v and t. We're trying to find a. When we look at the equations, the equation that's got u and v and t and a in is the first one. So if we use that equation, put in the values for u and v and t, we should be able to find a. Now, of course, you might also remember just the definition of acceleration as being change in velocity divided by time. So you might use this equation in a different form without actually realising this is the equation you're using. Part B of question 1 is also a SUVAT question. So as before, best way to start is to fill in the SUVAT values. So this time, what does it say? Well, it tells us what the velocity is at the beginning of the question. So you could write it in. I'm just going to tick it so that we know it's a known thing. The speed it finishes up with, does it tell you the speed at the end? Well, it doesn't actually say what the speed is, but it gives the clue. It brakes sharply to a standstill. So if it's come to a standstill, we know what the velocity is, so you can write in the value there. And again, we know the time that it takes. The question asks for the deceleration. Well, obviously deceleration, it's really just that's the acceleration. We know it's slowing down, so we know that the acceleration will be negative, and that's what we're trying to find. Trying to find the acceleration. It will be negative. Because it's negative, if you wanted, you could call it deceleration. Personally, I don't see the need for the word deceleration. I'm quite happy knowing that the acceleration is negative. But you've got to be able to cope with both ways of asking it. So you try to find acceleration. You know u and v and t. So basically, it's just like the previous part of the same question. Question 2 is again a SUVAT question. So we should be getting really into the habit of writing down SUVAT. Let's see what is given. It accelerates from a velocity of 2.5 meters per second. So that's the velocity at the start of the question. That's u, so u is known. You write it in, I'm just ticking it off to say that we know it. It tells you the velocity that it reaches. So that's like the second velocity in the question, so that's what we call v. So v is also known. You write it in. And it tells you how long this takes. So the time is known, and we're asked to find the acceleration. So we need to look at our equations. U and v and t are known. We're trying to find a. Which of the four equations is the one to use when you know u and v and t and you want to find a? Well, it's that one again. Through the second part, we now know the acceleration because we've just worked it out. And the velocity at the start of this extra 2 seconds, in other words, the value of u for the second part of the question, well, that's what the velocity was at the end of the first part. So we know the value to put in for u. The value for v at the end of the second part of the question is what we're looking for. And the time is given in the question. It's an extra 2 seconds. So that's going to be the time that goes in there. So we know u and a and t, we're trying to find v. Look at our list of equations, and there's one there that should cry out to us as the one to use if you know u and a and t and you want to find v. So we use that one. So question 3 asks you to sketch a graph. And even though it says sketch, you should still be drawing it with a pencil and a ruler, trying to make it reasonably neat. So what does it say? It says it starts at rest and 20 seconds later it tells you what the velocity is. So it starts at rest, and if each of these is 10, 20 seconds later it's got the velocity that it gives. And it says that it's accelerating uniformly. So if the acceleration is uniform, you should be able to work out what shape do you draw between the starting value and the final value if it's uniform. Not going to tell you, quite easy, you should be able to draw that. It then travels at constant velocity. So if at constant velocity of 12 metres per second, so it means that 40 seconds later the velocity is still the same as it was. Constant velocity doesn't go up, doesn't go down, so that tells you what to draw between those 2 points. And finally, it decelerates to rest, and that takes another 30 seconds. So we know it's going to finish up back there. It decelerates uniformly, so the speed goes from being there down to being there, and it changes uniformly. So it should be quite easy for you to work out what you have to draw between that point and that point. Not going to tell you, it's too easy. The question then asks you to calculate the acceleration in each part of the journey. So if you remember that acceleration means change in velocity divided by time, then you've got 3 different values. For this part of the graph, where it's speeding up, you can find an acceleration. And because it's speeding up, of course, you expect to get a positive answer. So change in velocity divided by time for that one. For the middle section of your graph, where the velocity is constant, so it isn't speeding up and it isn't slowing down, well, it should be pretty easy what the acceleration is for that one. Which takes a bit of thinking, doesn't really take any working out at all. And then for the last section, it's slowing down. When something's slowing down, we know that its acceleration is negative. So we expect a negative answer for acceleration, and we know how much the velocity changes by, we know how long that change takes. This is the last 30 seconds, so we should be able to work out the acceleration for the final bit. Quite straightforward. It will be negative, of course. Because it's negative, if we wanted to, we could call it a deceleration, but there's no need for that extra word. A negative acceleration tells us that something is slowing down. Question 4 gives us a graph that shows how the velocity of something changes. And this question requires us to describe. So describe how the velocity of the object changed. You need to give as much detail as you can. Clearly, to begin with, the velocity is increasing, and it increases more and more slowly, and eventually it reaches a value where it's not increasing anymore. So you need to write that down very clearly, as much detail as you can. How does the acceleration change? Well, remember, if the velocity is increasing quickly, you've got a big acceleration. If the velocity is increasing slowly, you've got a small acceleration. And if the velocity isn't increasing at all, you haven't got any acceleration. So you need to describe what's going on there using those ideas as clearly as you can, explaining what happens to the acceleration as time goes by.